How are you today? Today we are going to discuss on substrate effects on SN1 reactions. We've done the same for SN2 reactions. The rate determining step in SN1 reactions is ionization to form a carbocation, a strongly endothermic process, and we've said this is the slowest step and therefore it's the rate determining step. The transition step for this endothermic process resembles the carbocation. Consequently, the rate of SN1 reactions depends strongly on the carbocation stability. We saw that alkyl groups stabilize carbocations by donating electrons through sigma bonds, that is by inductive effect, and also through overlap of filled orbitals with empty p orbital of the carbocation through hyperconjugation. Therefore, highly substituted carbocations are more stable than those which are not highly substituted. So this is an example. So you have the carbon which is bearing the positive charge. This is a structure and it's usually sp2 hybridized, and the hybrid orbitals are usually on the same plane and 120 degrees apart. If you remember, you are SCH1 or 2, and the p orbital is always perpendicular to, when you have a carbon which is sp2 hybridized, it always has a p orbital perpendicular to the plane of the hybrid orbitals. And when it has a positive charge, then it means it's empty. When it is not positively charged, then it could be having one electron which needs to be stabilized or to pair with another, to be shared with another to form a covalent bond. So in this particular case, a carbocation, this is a structure. So this is empty lobe, and this is a p orbital. Remember, p orbital usually has two lobes. So the two lobes are both empty. They don't have any electron. Then adjacent carbon, in this case, this carbon is bonded to oxygen. Also, this is bonded to, sorry, not oxygen, but hydrogen. This is also bonded to hydrogen, and also it's bonded to hydrogen. And remember, this carbon here, when it has 4 single covalent bonds, it's usually sp3 hybridized. So it's the sp3 hybrid orbital of this carbon is overlapping with sp2 hybridized orbital of this adjacent carbon, because this adjacent carbon is sp2 hybridized because it's bearing a positive charge. So that forms that covalent bond. Then the other sp3 hybridized orbital of this carbon is overlapping with s of hydrogen, and of course they now share 2 electrons of the covalent bond. And similarly, this sp3 hybridized orbital of this carbon is overlapping with s of this hydrogen to form that covalent bond. Similarly, this sp3 is overlapping with s. Of course, when they're overlapping, they are donating 1 electron to form this covalent bond. So you can see there all 1, 2, 3, and these 4 covalent bonds. So the most important to note here is that out of these bonds to all these hybridized orbitals of carbon to hydrogen, which is S of hydrogen, which overlaps to form the covalent bond. Out of these bonds to hydrogen, there will be one which is in the right orientation with the p orbital of this adjacent carbon, empty p orbital. So it will overlap and tend to share the 2 electrons of this covalent bond with the adjacent carbon, the p orbital of the adjacent carbon atom, which is having no electrons. So that way, it will try to stabilize that reduce the positive charge by donating some electrons. So the positive charge is reduced. That's why that is how the alkyl groups are able to stabilize the carbocations by donating electrons of the adjacent carbons through the covalent bonds